350 kilowatts of fast charge power. From one silicon carbide box. No room-sized copper transformer, no separate rectifier cabinet. One silicon carbide box turns grid voltage straight into charging power. Here is exactly how it works. Here is the problem. Fast chargers in AI data halls want enormous DC power, and they want it now. But the old way of getting there is heavy, wastes energy as heat, and takes months to hook up. Chargers past 350 kilowatts and multi-megawatt data halls have simply outgrown the humble iron transformer. Why? Start with the old path so the leap makes sense. The power line coming down your street is medium voltage, around 13.8 kilovolts, far too much for any car. A distribution transformer steps that down to about 480 volts a C. Then a separate rectifier turns that a C into the DC a battery actually drinks. 3 big jobs, 3 separate boxes. Now the costs. That iron and copper transformer weighs thousands of kilograms. Think a small car's worth of metal bolted to a pad. It is genuinely good at its one trick, about 97 to 98% efficient. But it is a dumb block. It cannot regulate the voltage, it cannot smooth a messy load, and it cannot push power backward. Whatever comes in steps down and leaves, that is all it does. Hang a 350 kilowatt charger off it, and you also need the rectifier, the filters, the protection gear, each its own cabinet on the pad. So the real footprint is not one box. It is a room. But if size is the enemy, what actually makes a transformer that big? Here is the trick that unlocks everything. A transformer's size is set by how fast the electricity wiggles back and forth, its frequency. The grid wiggles at 60 times a second, 60 hertz. And there is a rule buried in the physics. The size of the magnetic core you need falls as the frequency rises. Slow wiggle, giant core. Fast wiggle, tiny core. So do not fight the size. Change the frequency. Take the grid's lazy 60 Hz and chop it into tens of thousands of wiggles a second, tens of kilohertz. At that speed, the magnetic core that once needed a room shrinks to something you could carry in one hand. Same power through it. Same job done. A briefcase-sized high-frequency transformer moves the megawatts that the room-sized one did. Picture stirring a bucket. Slow, wide strokes need a huge paddle. Tiny, fast flicks move the same water with a spoon. Frequency is the flick rate, and it lets you trade a room of iron for a handful. But here is the catch. Nothing on the grid naturally wiggles that fast. You have to chop it thousands of times a second at brutal voltage. What survives that? Meet the material that survives it, silicon carbide. For decades, the switches that chop power were made of plain silicon. They work, but at high speed and high voltage, they leak energy as heat every time they flip. And they flip thousands of times a second. Cook a silicon switch hard enough and it fails. Silicon carbide is a tougher crystal. A switch built from it, a silicon carbide MOSFET, flips faster, blocks much higher voltage, and wastes far less energy in each flip than the old silicon workhorses. Less heat per flip means you can flip more often without melting the box. That is the whole game. Speed needs low switching loss, and silicon carbide is what delivers it. Run the chopping at tens of kilohertz and hold off thousands of volts at the same time, all without cooking itself. That combination is what pushes the whole box toward 99% efficient, better than the iron block it replaces in a fraction of the space. So we have a fast switch and a tiny transformer. Now how do you wire them into one box that eats grid voltage and spits out clean 350 kilowatt DC? Now walk the whole chain front to back. Medium voltage, a C comes in off the line. First, silicon carbide stages rectify and chop it. They flip that incoming power into fast, high-frequency a C at tens of kilohertz. That fast a C feeds the compact high-frequency transformer, which does 2 jobs at once. It steps the voltage down and it isolates the car from the raw grid so a fault upstream cannot reach the vehicle. On the far side, one more rectifier stage flattens it into a steady, regulated DC bus. The clean voltage the charger or the data hall plugs into. Grid a C in, controlled DC out through a box the size of a cabinet. But 13.8 kilovolts is a lot for any single switch to face. Here is the clever part. Instead of one heroic switch taking the full hit, the box stacks many small modular cells in series, like batteries in a flashlight. Each cell holds only a thin slice of the total voltage, a few hundred volts, well inside what one silicon carbide stage can handle. Stack enough slices and together they span the full medium voltage safely. Modular, repeatable, and if one cell needs service, you are not rebuilding a monolith. That is the signal chain. So what do you actually gain from doing it all in silicon? Here is the real payoff of doing it in silicon, the box thinks. The old iron transformer was a dumb pipe. This one is a controller. Because software commands those fast switches thousands of times a second, the box can actively hold the output voltage steady even as demand jumps. It can clean up the power factor, squaring up messy current so the grid is not dragged out of shape by the load. And because switches flip both directions, power can flow backward, not just forward. That is the door to vehicle to grid. a parked EV feeding energy back when the grid is strained, or a battery buffer soaking up a spike so the data hall never flickers. One controllable box now does what used to take 3 specialists. The transformer that stepped voltage down, the rectifier that made DC, and the rack of power quality gear that cleaned and stabilized it. Fold all 3 into a single programmable unit and you do not just shrink the footprint. You gain a knob for every one of those jobs. So picture it all snapping together. So here is the full picture. One silicon carbide box about the footprint of a cabinet takes 13.8 kilovolts straight off the medium voltage line and feeds 350 kilowatts into a fast charge stall, or backs a multi-megawatt data hall. It is smaller than the room of iron it replaces, runs near 99% efficient, and it is grid smart, regulating, cleaning, and reversing power on command. That is the master trick. Change the frequency so the magnetics shrink, then use silicon carbide to survive the speed, and suddenly one programmable box swallows a whole equipment yard. Now honestly, the trade-offs. This box costs more upfront than a dumb iron transformer, and it is far more complex. More parts, more software, more that can go wrong. So it wins exactly where its strengths pay for themselves, where you need dense power, tight control, and two-way flow in a small footprint. A crowded charging plaza, a packed data hall. That is the box. The next place this box is headed is bigger still. Megawatt charging for electric trucks, and power feeding straight into data centers where every square foot of floor is worth a fortune. Same trick, larger stack. If this opened the box for you, the next one worth opening is the battery it feeds. Why fast charging heats a pack, and how the car keeps it from frying. That is where we head next.